Not speaking about the de Sitter space, which was all we heard about in the first days of the school. So what I want to do in this set of lectures is to tell you about how we learn about the various properties of the universe, parameters that we use to characterize it, mainly through the CMB and large-scale structure measurements. So these days we have a very good model for cosmology after inflation, if you want, or after the Big Bang. It's a 6-parameter model with pretty well-determined parameters, and they have been determined using primarily, although not exclusively, measurements of the cosmic microwave background and large-scale structure, also supernovae measurements, et cetera, et cetera. So what I want to do in these lectures is walk you through the basic physics that goes into doing this type of calculations of what you might expect for the statistical properties of the CMB maps if you started with the initial conditions that we've been discussing in the previous lectures, and how we can, or equivalently, how we can go back from what we see in the cosmic microwave background and large-scale structure and so on, and try to infer the initial conditions of the universe, or what came out of inflation, or whatever came before the Big Bang. So let me start by so today I'll start by doing some simple introduction, and then I'll start talking more carefully about the cosmic microwave background. And later, in the next few lectures, I will talk about large-scale structure, and we'll see as we go along. But so let me just give you, for the purposes of, so that we are all on the same page, basic facts about our universe, the homogeneous universe, the basic properties about different structures that we see, and so on. I did produce a little set of plots that I hope was handed out to you. I didn't want to lower the screen every so often, but I thought it was interesting to just look at some of those plots. So let's start by just the basic facts. We seem to live in a Friedmann-Robertson-Walker universe. That seems to describe very well what we see in terms of the overall geometry of the universe. In general, we could consider FRW universe, curved FRW universe, but for the most part in these lectures, I will consider the case of flat FRW universe with k equals to 0, which very well describes our universe. So that's will be, for the most part, the starting point. This universe is filled with stuff, okay? It's filled with matter of various kinds. So at least we know, well, it's filled with radiation, the CMB, so it's filled with a lot of things. It's filled with radiation, like the CMB, and a background of neutrinos, we think. It's filled with matter. This matter, at least, is composed of just our regular matter that we typically label, we call them baryons. So it's just atoms, electrons, etc., but we call them baryons. So baryons. And we are for sure, it's clear that it's also filled with something else, cold dark matter, so it's filled with a lot of dark matter, and I will, part of the lectures will be going through some of the evidence, at least in what pertains to large-scale structure and the CMB, that the universe is indeed filled with dark matter, although we probably know this, or we knew this from before. And we now also know that the universe currently, a big chunk of its energy budget is given by a cosmological constant or something that looks very much like it. So these different types of matter that the universe is filled with obey what we usually call different equations of state, so a relation between its pressure and its energy density. So something like radiation has a pressure which is 1/3 of energy density, so W is 1/3 for radiation. In the case of non-relativistic matter, this W is basically given by the, say in a gas, it's just the typical velocity of the particles in the gas divided by the speed of light. So for a non-relativistic gas, this is very close to 0. It's given by kT over the typical mass of the particles for some gas in thermal equilibrium. So for matter, you can take this to be very close to 0, and in the case of the cosmological constant, the pressure is minus the energy density, so W is very close to -1. So if you use just energy conservation for these different I've been making fun of the different speakers having to go up and down, but this is obviously going to happen to me instantly. I now sympathize with them. Okay, so if you just use energy conservation for this, you can in the FRW background, you discover that you discover this. And so if you know where h is the Hubble parameter, the time derivative of the scale factor a of t, a dot over a, and the current value of the Hubble parameter, so this thing at the current time is usually called the Hubble constant. So if you just use this equation and a simple relation between P and rho, you can discover that for radiation, the energy density scales as a to the -3. I mean, these are things that you all know, but I'm getting to some point. Sorry, thank you. You see, everybody knows except of me. A to the -3, and for the cosmological constant, rho is constant. Okay. So, okay, so this you all know, and and this, of course, simple interpretation. So, non-relativistic particle, the energy density is just carried by the mass, and so this is just the dilution of the number density of these particles as the universe expands. This is the same thing for the relativistic particles plus the redshift of their typical energy, and well, the cosmological constant is just constant. But the okay, so this you already knew. But the point I wrote this to make the following point: these different forms of matter in the universe, its energy density scales with the scale factor in different ways. The universe has expanded by a huge amount, okay, since the Big Bang, and so these different components have dominated the energy density of the universe in different times. If you go sufficiently back in time, A sufficiently small, radiation will be the dominant one, then matter, and then the cosmological constant. That's what happened in our universe. And so this is important in the following sense. So as we have been discussing, the initial conditions for perturbations in our universe are what the previous speaker called scale invariant, okay? However, our universe, the time evolution of our universe will imprint in this scale invariant spectrum a lot of scales. In particular, for example, there is a specific time in the history of the universe in which the density of matter and radiation are equal. That's called matter-radiation equality. And so depending on whether you are looking at perturbations whose size is larger or smaller compared to the Hubble size or the Hubble horizon at this particular time, well, these perturbations will behave differently if they are larger or smaller than the horizon at the time of matter-radiation equality. And so what we see at the end through the process of structure formation will have imprinted information about exactly when this happened by looking at the behavior of how, as a function of scale, the amplitude of fluctuations, for example, will have in it evidence for this transition and this transition. So this is just an example of how we will go about determining the amount of matter and, well, radiation, at least for the part of the CMB, we see directly, but not maybe the background of neutrinos. So the amount of matter and radiation that there is in our universe by locating this, or by understanding these effects that break the initial scale invariant and imprint specific scales in the dynamics of the perturbations, that then we can go out and measure and then determine when these things happen. Okay? And so I think I did, one of these handouts, the first plot is the very simple plot of just density. It's just these power laws, but so that you have with some scales so that you can see when, of course, I didn't even go so far back in temperature, and you can see that how density changed by many, many orders of magnitude, and how there are these transitions between one thing dominating and the other thing at later times. And the other, of course, the other consequence of these very rapid changes maybe they are not rapid, but very vast changes in the typical densities and temperatures in the universe as time goes by is the fact that if you go back in time, densities are so high, temperatures are also so high that you're typically in thermal equilibrium. But as you go on, as you progress in times and things become more dilute, many times rates of various processes become longer than the Hubble time, and certain things do not longer happen efficiently, and you have various freeze-out processes and various falling out of equilibrium processes. For us, in our lectures, the one example of something changing due to the change in the temperature of the universe will be recombination. That will be very important for us, and that leading the universe to become transparent. So we will talk about that in a second. But it's also another of the consequences of this changing universe. It changes slowly, but even so, it has been around for such a long time that the typical conditions have changed a lot. Okay, so and of course, in addition to just this, you can use Einstein's equations to find the evolution of the scale factor with time, which you also know. So you can use Friedman equation plus the curvature piece that I'm neglecting from now on. You can use this if you know that rho now goes as a particular power of A. You can solve this equation to determine how A goes as a function of time. And so okay, so you all know this, but let me just. So in the radiation era, A goes as T to the 1/2. In the matter era, it goes as T to the 2/3, and in a period dominated by the cosmological constant. It's just an expression. Okay, good. So the only other piece of of jargon that I write this also to incorporate. So in this Friedman equation, okay, there's the density then is made up of these various different components. There's the radiation, there's matter, there's the cosmological constant, etc., etc. If there's a neutrinos might be inside of the radiation. Any component that you want is in here, and you can even call the curvature piece a rho curvature and put it inside there. And what's typically done, I'm just, because it will appear in some of the later discussion, is divide this whole equation by h squared, and this quantity over here is, h squared. This quantity over here is called rho critical density, and the ratio of the different, and it's just the typical density that you can make up by using Newton's constant and the Hubble constant, or the Hubble parameter, and then you can, the ratios of these different components to rho critical are called omegas. So for example, omega in matter is rho matter over rho critical, etc. And by definition then, because I just divided by a square, all of these omegas add up to 1. Okay? Now, the one thing to point out that will be important when we discuss the CMB to understand parameter dependencies is that these omegas are then the ratios of a physical density to this critical density formed by the Hubble constant. So, or in other words, if you want to know if you want to know the physical density, is not just given by omega. It's given by omega times something that is proportional to the Hubble constant square. So a physical density is proportional to the parameter omega matter, or omega, whichever the omegas it is, times h squared, with the little h is is by convention the Hubble constant today, divided by a typical value of 100 kilometers per second per megaparsec. So this combination of parameters, so a physical density of some component is proportional to its omega times the Hubble constant square. So omega is not really measuring actual physical density, but it's a ratio with something that was constructed with h squared. So, and this all is important because what you can determine with the CMB, or what you can determine by looking, for example, if you were to determine at what time matter radiation equality occurred, we can measure the radiation energy density using the temperature of the CMB. So we know it in physical units, T to the fourth. And so if we were to know the ratio of matter and radiation, for example, which is something we can determine with the CMB, we would know the amount of matter in physical units, in grams per cubic centimeter. We wouldn't know the omega in matter, because in order to compute the omega in matter, we need to know Hubble constant. So omegas depend on the Hubble constant. Actual physical densities are omegas times h squared. Okay? So for the most part, a lot of these physical processes, all of these physical processes that will imprint scales in the problem will depend on the actual densities, not on some omegas. Okay? And so we will be able to determine not omegas, but omegas h squares. And this leads to the fact that there are certain combinations of parameters that the CMB cannot determine. It can determine this very well, but it cannot determine separately omega and h. Okay? That's the reason I'm going through this. Okay. Any questions about this so far? No? Okay. Yeah? Yeah, so we will talk about it. So if you look at the way I made the plot on the because I put log scale, this equality, and I did it in terms of temperature, this equality between the cosmological constant and the matter that is happening around redshift of 1 or around now looks like a tiny thing, irrelevant there in the corner, although you can not use log scale, and this takes most of the time of the history of the universe, and so it will be the most important thing happening in the plot. It does affect things. It affects, for example, the rate at which structure can grow or not grow during a period of in which the energy density is dominated by a cosmological constant. Pretty much structure formation stops. And so it does lead to consequences, and when we talk about large-scale structure, we will see that. Now, as to why this coincidence happens now, I'd rather not go into this, into this. Yeah, into this. I don't know. It's a coincidence. Fortunate for us, maybe, but. Okay, so good. So the other thing that I wanted to do, and you've already done this in the other situation, is look at just introduce conformal time as you did in the previous lectures. This is very useful for looking at how light rays travel, where they get to, and so on, because they just, if you measure time in conformal time, they just travel at 45 degrees in your diagrams. And because for us, we will be pretty much trying to think about what we can see using light rays, the CMB or the light emitted from galaxies and so on. It's also useful for us. So what we want to do is then write the FRW metric as something like a square of conformal time, which I will call tau. So now light rays again travel at 45 degrees in your diagram, and just as before, a of tau or d tau is dt. Okay, so you can find the conformal d tau by integrating this equation. Okay? And so, for example, in the simple examples that we had before, where a of t, so for the most part, for the next lecture, so I will mainly be talking about the CMB, so I will be talking mainly about the matter era and radiation era, in which the scale factor goes as t to some power with a power that it is less than 1. And so, for example, if you just do this estimate, so what you get here for a power law is this. This is tau. And in particular, for example, in the radiation era, A is proportional to t to the 1/2. And so tau is proportional to A. Okay? So the important thing that we discover about periods in the history of the universe when it's expanding in this way is that A equals 0, time equals 0, the Big Bang corresponds to a finite value of the conformal time as well. So tau goes to 0 when A goes to 0. This happens whenever P is smaller than 1 there. And so if we do our little conformal diagram here with our current time, tau naught here, we have our 45-degree lines of photons. Let me just do it in 1 dimension. That's all I can master. So when we look back in time, there's just a finite distance that light rays can travel in until t equals to 0. Okay, and so of course, in these 1 dimensions, this would just correspond to the two poles like that or something. In reality, it's an entire sphere. Okay, but But there's just a finite distance up to which you can see things, okay? And of course, this was the source of, so this is the Big Bang. This was the source of the so-called horizon problem, which was the fact that when you say look at, so the CMB does not come all the way from the Big Bang. It comes from around a redshift of 1,000. So this says the conformal time from where we see the CMB. This is pretty much as far as we can see. And we can imagine seeing, even if we were to detect neutrinos from cosmological neutrinos and use them to make maps, because they have a mass, they really come from much closer by. So only if there were some sources of gravitational waves for which the universe was transparent before, we might be able to see even before this time. But in any case, when you look at the CMB, say in this one-dimensional example, you can see two spots, only one in that direction and one in the other direction, corresponding to the time of the recombination. We will go through this in more detail. But the point is that because there's a finite range of time in this, or range of tau in this diagram, this point and this point were not in causal contact at the time that the CMB was emitted to us. So we look at this point in space-time and this other point in space-time when we look in the two opposite directions. There's only a finite amount of conformal time from here until the Big Bang. So light rays from this point cannot get to the other one, and so they could not have talked to each other. Why does the CMB have the same temperature, and so on? So that was the classical horizon problem, which was solved or is solved in the context of inflation by just extending this diagram back, such that these points eventually can talk to each other. Okay. So the part of slow roll inflation that you've discussed in the previous lectures is just extending our times back so that different places can talk to each other, and maybe when they talk to each other, so there was some mechanism to create these perturbations that will lead to structure as we see it. So let me just say one more thing about this. So another just simple way of stating the same thing is to ask the following question. Imagine some two locations in the universe separated by some physical distance, L physical, which is given by the scale factor times their comoving separation. So we take 2 points moving with the Hubble expansion, so they are at a fixed comoving separation. Their physical separation is scaling with time like that. So as you go back in time, these 2 points are getting closer together, okay? Because A of t is going to 0, so everything is closer. 2 points are closer together. But if you compare this distance not with not the physical distance, but if you just compare this with the age of the universe up at a given time, so if you do this physical distance divided by time, so how separated they are in units of the age of the universe, well, this is just proportional to A of t divided by t, or equivalently A of t times the Hubble constant. This thing is nothing other than the conformal time there, so A of, or inverse, right? So in this type of universes that we're talking about, radiation era or matter era, A of t is going as t to 1/2, t to the 2/3. This is smaller than t. So as you go back in time, things are more separated in units of the age of the universe than before. So in units of the age of the universe, it's just in units of what's left here in the conformal diagram. Okay, so at 2 points, as you go back, they are more and more separated by relative to each other in units of this. So this is just, again, the horizon problem, but just to state it in some other ways, even though everything is 2 points are closer together in the past, they're in some sense further away if you measure it in units of the age of the universe up to that given time. And this, and equivalently, this A of t times h is just given by a dot, okay, because h is a dot over a. So this thing is just a dot. Okay, and so if you want to, so whether or not this happens, whether things are getting further away in units of the age of the universe or not, all depends then on the sign, on whether a dot is increasing or decreasing, or equivalently on the sign of a double dot. So you can use the Friedman equations to find that a double dot over a is proportional to rho plus 3p. Okay? And so if you want to have a double dot negative in order to save this horizon problem, you need to have p more negative than minus a third of rho. Okay? So when you do that, you go from one regime to the other. Inflation in particular has p very close to minus rho, so this is indeed I'm missing a minus sign though. Because if not, everything looks the opposite. Okay, so sounds good. So okay. Any questions about this so far? No? I'm just trying to set some basic things before we start doing calculations. Okay, so the other thing that I did in these notes, just so that you also get a sense of numbers, okay, because well, that's also useful to have some sense of actual numbers in megaparsecs or in whatever unit you prefer. So a parsec is 3 times 10 to the 18 centimeters, and it's a unit of distance used in astronomy a lot, and it corresponds to the distance to a star over which, when the Earth goes around the sun, the parallax on the sky of this star located at 1 parsec is 1 arcsecond. That's the reason they introduced this distance. So in this little table, I just did the following exercise. So just compute. So as we said, imagine that you're at the center here and you look out, okay? And we are looking, this is in conformal, so this x, this is the plane of x and y, just 2 of the dimensions of space in conformal coordinates. Okay, from the Big Bang, you can only look so far, okay, because of the finite conformal distance that light can travel. So I just made a list, a table, so that you can get some orders of magnitude of how far this is as a function of redshift. Maybe I didn't define redshift, but A of t probably divided by A today is defined as 1 plus the redshift z, okay? But usually the value of the scale factor today, or I will take to be 1. It's just you can take whatever convention you like, but usually I'll take it to be 1. So just for fun, there's a list there of age of the universe for various redshifts. So redshift 0, the age of the universe is like 14 gigayears. And then also then various redshifts and the distance out to which you can see in this Hubble volume, just so that you get a sense of things, okay? And I picked some random numbers there, except for redshift z of 1100. That's from where the CMB is coming from. Redshift 1 or 3, this is the typical redshift of, well, maybe a redshift of 0.1 is the typical redshift out to which 0.1, 0.2, the typical redshift up to which people make maps of of the location of nearby galaxies to study the large-scale structure of the universe. And you can see that, well, if you can go all the way up to the Big Bang, this distance is around 14 gigaparsecs. But if you go up to redshift of 0.1, you're only going, so at z of 0.1, you're only going roughly a fourth of a gigaparsec. But by the time you get to redshift of 11,000, the CMB, you've gone, most of your way out. It's already 13.9 gigaparsecs. These are numbers just for the standard cosmology of WMAP, okay? And redshift of 1100 corresponds to 380,000 years after the Big Bang, okay? So the CMB will come from this redshift, and it's almost all the way out to where you could see it has even, there's another column with how much of the total volume enclosed in our Hubble patch is enclosed up to that distance. And you can see that most of the volume is up to there. And you can also see that you already get half the volume by the time you go to redshift around 3, or half the distance, okay? Okay, so, and the other plot that I wanted to discuss, okay, so now I need to figure out a system for when I used all of the black, although I didn't use this one. Okay, so the other plot that I wanted to discuss is one that says horizon scale. So this is just so that you get a sense of so this is what is done in this plot. So the first thing that, so what is plotted, the line there, so this is just time in the universe as measured with temperature. And this is the size of the Hubble scale in comoving coordinates. So it's just 1 over h a, okay? That's so that's the size of the horizon in comoving coordinates at different times, and you can see it grows in our universe, at least in the radiation era and the matter era. And you can see that there is a break in this power law. It grows in different ways. In the later time, when the universe was dominated by matter, it has one slope. When it was dominated by radiation, it had another slope, okay? So that crossover is what's called the epoch of matter-radiation equality. And so on the x-axis, I've labeled this distance by megaparsec. On the other side, what I did is compute how much mass is enclosed inside of that horizon, okay? Very simple, just density of the universe times h cubed, okay? It's how much mass it's enclosed inside of that horizon. And I label it in terms of solar masses so that you can see, compare this with typical masses of things, okay? And I label there, roughly speaking, how much is a galaxy, how much is a cluster of galaxies. So just to take, okay, so just so that you get a sense of the following fact. If you imagine a galaxy, for example, a galaxy is some sort of overdense region. Why did it end up being like that? It started as a small overdense region. It collapsed to form this galaxy. There was a time when the size of this overdense region was comparable to the size of the horizon. That, for a galaxy, and also for a cluster of galaxies, happens during the epoch in which the universe is radiation dominated, okay? So as you go to larger and larger scales, the wavelength becomes comparable to the horizon eventually when you go into the matter era. The range of scales that we can measure using the CMB and large-scale structure is more or less labeled there with the approximate range is labeled there on the other side. And you can see that we can map both with the CMB and large-scale structure ranges of scales that were comparable to the horizon. The smaller scales were comparable to the horizon during the radiation era, the larger scales during the matter era. So we get to see this transition, okay? So we get to determine by studying the dynamics of these perturbations when this transition actually happens. That's how we will do it. Okay? Good. So let's talk a little bit about these inhomogeneities in the universe. Okay? So some of you came to this movie that we projected last Tuesday, and there you saw all kinds of NASA animations of the formation of structures and stuff like this. So I don't feel so bad that I'm not showing them to you with the computer today. But what we think happened then in the history of our universe is that we started the universe, or we didn't start the universe. The universe started, at least in what's, for me, the universe starts in the radiation era, and at least for the context of these lectures. Okay, so the universe starts in the radiation era, and we now know that at that time, the universe was not perfectly homogeneous. That universe had small fluctuations, perhaps imprinted by inflation. And I will hopefully tell you the evidence that we have that that's the case. That's pretty compelling evidence. So the universe started with some small fluctuations. The size of the temperature differences in the CMB is around 10 to the minus 5, 10 to the minus 4. And so we start with a universe with these small fluctuations that they grow by gravitational instability, which we will also study in the course of these lectures a little bit, until they form objects, okay? And these objects are, I will stop at the scale of galaxies. We started today with stars, but I will stop at, the smallest thing I will talk about is a galaxy. So forms galaxies. These galaxies sometimes live in groups of galaxies or clusters of galaxies. They form all kind of filamentary structure and so on. And even though this universe started, as I said, with a scale invariant spectrum of perturbations, there was a lot of scales imprinted into these objects. And you can see this, for example, quite clearly if you just look at the gravitational potential of the various objects. So these initial density fluctuations had, as I said, were of order 10 to the minus 5 or so. So gravitational potential fluctuations were of order 10 to the minus 5. But at the end of the day, for example, we move in our galaxy at 200 kilometers or 220 kilometers per second, roughly speaking. So the size of the gravitational potential is V over c squared. That's much smaller than 10 to the minus 5. So for some reason, and as we will see when we discuss gravitational potential during the matter era, for example, remains pretty much constant. So the reason why, in the end of the day, we are not moving with typical velocities given by 10 to the, or square root of 10 to the minus 5 times the speed of light, is because the universe went through a period of radiation domination. If you go to larger objects like clusters of galaxies, their typical velocities are typical velocities of things moving in a cluster of galaxies more like 1,000 kilometers per second, and this will have to do all with this fact of matter radiation equality. So hopefully we will get to discuss that as we talk about structure formation. But starting with scale invariant initial conditions. The evolution of the universe imprints a lot of scales on it. Some of them are easy, and I will talk mainly about the easy ones. Matter radiation equality, maybe the transition between dark energy and matter and so on. These are the easy ones, the ones that you get in linear theory, all that I can do. Then it becomes a mess, stars and so on. It's much more complicated, and so there are many more, and the dust, instance, there are many more scales and many more things as you go to smaller and smaller scales, more complicated. You need to know more and more phenomenology to figure all of that out. To some extent, it's not that we have figured it out. Okay, and so we know the universe started with some initial perturbations, and as far as we can tell, these initial perturbations were scale invariant, almost. And all of the scales that we see, at least where we can both calculate and measure accurately, were imprinted, we think, by just these processes like matter radiation equality. We don't have much of an evidence of the initial fluctuations not being scale invariant. And also, also true, these perturbations started, they were both, as far as we can say today, Gaussian. Initial conditions were Gaussian. We don't have evidence that there's any departure from just Gaussian statistics for these perturbations. Nor we have any evidence that these perturbations involved any kind of perturbations in composition, so-called isocurvature perturbations. So our universe, as we said, is made up of a lot of stuff. So you could imagine that its fluctuation, there's different amount of these components in different locations, but the relative composition of them could also be different in different places. So it could be that you start in a region with more dark matter relative to baryons, and in the other place more baryons relative to dark matter, in such a way that the total density of these two components were almost uniform everywhere, but there were changes in the composition. So because there are many components, there's the neutrinos, the dark matter, and so on, you can imagine a lot of these possible fluctuations in the composition. No evidence that in fact, good evidence that there's no such thing. Okay, for most of these examples of fluctuations in the composition. So it looks like with the universe started in a very, if it had to choose the initial conditions, they look like the simplest, at least to describe the simplest. Scale invariant, no fluctuations in the composition, Gaussian, etc. So that's this, and as far as we can tell, then all of the different scales that we actually observe were imprinted as a result of the evolution. So basically, the basic structure of what we are going to be doing is there are some initial conditions, okay, set by inflation or what have you. So we know they were there at the beginning of the Big Bang. There's some dynamical processes, matter radiation equality, whatever, that make these that make the different components evolve in different ways. And so if you look at if you were sitting at the universe in some particular point in time, for example, at the epoch of recombination or at the epoch of matter radiation equality, you would see something. You would see not a uniform universe, and that is related to these initial conditions in some way, and a lot of scales have been imprinted into this pattern of velocities and density fluctuations that you would observe if you were there, just through the dynamics of this plasma of matter with the radiation and the dark matter falling and making potential into potential wells, etc., etc. So all of these will imprint scales into this, and furthermore, then we are going to look at this so then we are going to look at it from redshift 0 from today, and basically there will be also a bunch of projection effects as to how we see ourselves the things that are happening here. So in our conformal diagram here, if so there's two parts to this story. First, or three parts. We have to characterize these initial conditions. Then we have to make them evolve. As we make them evolve, what's happening in the universe at this time, is related to the initial conditions in some way, involving the dynamics of all of these components. We have to calculate that. And then we also have to calculate how we see that, okay? Because there will be a lot of effects like gravitational redshift, angles, and stuff like this that we will need to figure out. And those various effects will also depend on some of these cosmological parameters. So we get information on the cosmological parameters through the different scales imprinted here by the dynamics, and also through various projection effects having to do with how distances scale, with cosmological parameters, with the matter, and lambda, and so on, and also how, or the redshift effects, and etc. So what I want to do then in the next, as we go along, is to set some examples of state the initial conditions, calculate at least as best I can do in the blackboard, and I also I'll make you do some of these things in the problems. Calculate the state of the universe, say for example at recombination, discuss the various scales that were imprinted here, then discuss what's the relation between what was happening there and what we observe. Okay? And that's how we will see how we determine various cosmological parameters. And in principle also, if we see that we understand these two things and everything fits, we might also be able to, or what we observe also depends on the initial conditions. Right? And this is where we will learn about inflation. So this is not a system that has evolved to some sort of state in which it forgets about the initial conditions. To the contrary, all that we see appears to be just related or a remnant of those initial conditions, at least on sufficiently large scales, which is where I will stick to. Any questions? So before I start with the CMB, let me just discuss a little bit this 6-parameter model, just the status of what we already know, just to point out a few things, okay, about these parameters. So we will do this, try to figure out how it is that we have figured out these parameters and so on, but let me just tell you a little bit about the outcome. So the first thing to know is that all the cosmological observations on large scales are very well described by just a 6-parameter model. Okay, probably I should call it a 7-parameter model because the 7th parameter is the current temperature of the CMB. We don't think of it as a parameter because it was measured much before, and so we always knew it was 2.7 Kelvin. So it's not a parameter, but it is a parameter, okay? So, but it has been measured directly before and not through the large-scale structure of the CMB, but just directly. So these 6 parameters, this current lambda CDM cosmology, these 6 parameters maybe can be divided into 3 groups. One of them has to do with just the matter content, okay? And it basically has to do with the fact that we are able to determine this epoch of matter radiation equality and so on. So the parameters are this omega matter times h squared, which is nothing other than the density in matter. The other parameter is what's called omega b h squared, so the density in baryons in units of the critical density. So just not in units of the critical density, but the physical in grams per cubic centimeter, if you want, not in units of the critical density of regular matter. So these are 2 of the parameters that you need, and then the value of the cosmological constant, or omega in the cosmological constant. These are the 3 parameters that you need to describe pretty much all of the observations on the large scales, the parameters that have to do with the matter content of the universe. Then there are parameters, as I said, having to do with the initial conditions, and these are just the amplitude and the slope. So as we were discussing before in the other lectures, probably it's a very good approximation that the spectrum of initial fluctuations is scale invariant, but not quite, because at least in the context of inflation has to end. So as you progress in time, the smaller and smaller fluctuations that are being created are also being created closer and closer to the end of inflation. So probably they don't have its properties do not need to be identical to the ones that were created before, but because everything is changing slowly with time, this is a small number, ns minus 1. Amplitude and slope of perturbations. And the slope is needed now. So we cannot take a scale invariant fluctuation. So maybe this is in terms of, I mean, it's needed at 3 sigma or something like that, or maybe a little bit more. But it is needed. Okay, we cannot assume the spectrum is perfect, is perfectly scale invariant. This scale invariant spectrum has a name that we usually like to call it. It's called the Harrison-Seldovich spectrum. And this reminds us of the fact that the scale invariant spectrum is not, was not proposed in the context of inflation, but it was proposed much before by both Harrison and Zeldovich independently, just based on very simple arguments. This is the spectrum in which you have equal amount of fluctuations on every scale. If you make them red, you screw up on the large scales, the metric fluctuations become very large and everything collapses into a black hole. And all large scale or small scales, depending on your tilt. So unless you do it very close to 1, you have some problem either on small scales or large scales. So that's roughly the argument that they used in the 70s, I believe. So, okay. So, and then we also need some astrophysical parameters. What I will call astrophysical parameters. In the context of this parameter model, is 6 parameter models is what's called the optical depth to the last scattering surface, tau. And the point is the following. Even though I said when we look at the CMB, the photons have been traveling from this recombination 380,000 years after the Big Bang to us, that's not quite true. There's a small fraction of the photons that have scattered with electrons that were around in the later universe, and we will discuss maybe a little bit later as to why that's the case. The first stars and galaxies emit UV radiation that ionizes the hydrogen again after recombination. These free electrons then provide a source of opacity for the photons, and so like a few percent or 10% of those photons scatter again. So when we look at the CMB, not all that we see, 90% or 90-something% is coming from redshift of 1100. The rest is coming from nearby. And we need this. This affects sufficiently our observations that we need to include it. We cannot say that, forget about it. Okay, so these are the 6 parameter model, and with this you can explain all of the observations pretty much. So let me. I've given you a few plots. So and I've taken most of these plots from the WMAP 7-year papers. There are later versions, but this is like the golden standard in that they don't feel that they need to be speculating about anything. So if you really want to get the conservative view about everything, how everything fits, you always go to the WMAP team. They don't, at this point in time, they don't need to discover, 1 sigma effects or 2 sigma effects to become famous. So, okay, so you can see the spectrum of temperature fluctuations, and the bottom one has to do with polarization. I will discuss the shape. The goal of these lectures will be to try to figure out this shape. But you can see it has very small error bars. It's not a scale invariant spectrum. It has all these wiggles, bumps and wiggles, and so on. And the heights of these bumps and wiggles depend on L and so on. All of that has to do with matter radiation equality, with the baryon density at the time, and so on. That's what we will try to sort out. And it's by looking at this shape that all of these parameters have been determined. Okay? And you can see in the table how well they are determined. They are determined pretty well. You can still ask the question, okay, even though, and this 6-parameter model, if you just ask the question, how well does it fit the data? It fits it very well. If you calculate some sort of chi-square, it's just fine. So everything is very nice in terms of WMAP, and also when you combine it with other experiments as well. You can still ask the question, okay, sure, this might be a good fit, but if I enlarge the size of the number of parameters, especially by enlarging it with some well-motivated parameter, do I get even a better fit? Do I have any evidence that there's something else other than this? For example, a background of gravitational waves that could be part of these initial conditions. Or maybe I can detect that the number of neutrinos, relativistic neutrinos, is not exactly 3. There's some extra species or something like that. Or that the neutrinos have a mass. We know they have a mass, but it's sufficiently large that it affects how structure formation goes. So I can add all of the parameters at the same time, and then I will not be able to say very much, but I could add 1 parameter at a time and see what happens. And so in this other plot, you will see some examples of those exercises in which you take this 6-parameter model, add one thing at a time, and see what happens. So, for example, in the context of the initial conditions, you can look at this plot and say, okay, let me add also the possibility that there are gravitational waves, okay, this R tensor to scalar spectrum that has been discussed in the previous lecture, and add this as a parameter. Do I have any, is there any good evidence for it? And we can rule out a big contribution of this. Small contributions we cannot rule out, but we don't need it for, it's not needed for fitting the data. Same thing with maybe the equation. So other things here are about whether this is a cosmological constant or not. So the thing that I want to impress upon you, and it would be good if you take some time to look at those WMAP papers, is that if you keep adding, at least if you do one parameter at a time, you don't find any evidence of, you don't need anything more than these 6 parameters. There's another plot that may be useful to look at, which is this one that shows the omega lambda and omega matter is in the x-axis, okay? So another question that you might ask, is the universe flat, okay? Is the curvature indeed 0, okay? So you can enlarge these parameters with adding one parameter more, for example, the curvature. And you can look at the constraints from WMAP, for example. And these are, this is shown in this plot here in the following way. So the solid line there is just flat universes. Omega matter plus omega lambda equals to 1, a 45-degree line there. All of the dots there are models that fit WMAP just fine, okay? So even though they have a very different omega matter and omega lambda, they fit WMAP equally well, okay? We will try to understand why that's the case. It's, I guess, one of the simplest things about the CMB that one can figure out, so I will use that as an example. So this also tells you that for some parameters, at least, WMAP by itself, or the CMB by itself, cannot tell you the answer, okay? There are parameter degeneracies. Now, as you move across this line, you're changing a lot what omega matter and omega lambda is, but keeping something that's measured by WMAP, which is the angle of the acoustic of these peaks in the CMB, you're keeping that fixed. So that's the location where that angle that is very well measured remains fixed, but still the parameters vary. But as we can also, by looking at the location of matter radiation equality even within WMAP, we can figure out this parameter very well. If you're changing omega matter, you have to compensate h in order to keep omega matter h square fixed, okay? Because this determines matter radiation equality, and it's determined very well, as we will also discuss. And so that's why they label these colors in these points with different colors according to their value of the Hubble constant. And you can see that if you want to go to larger values of omega matter, you need to have models with smaller and smaller Hubble constant. And it's just keeping this thing fixed. That's why it's moving like that, okay? So, of course, you can go out and measure the Hubble constant directly, and that puts it around 70, and that puts you right in the flat universe line. But in order to know that you are in a flat universe, you need additional information. That was the point that I wanted to make. Okay, and the last point that I wanted to make about data-related stuff, we saw in the movie, the ones that came to this movie at the end, after all of these trips to Antarctica and the balloon and so on, they mentioned the new experiment that Mark Devlin is working on, which is actually the experiment is led by Lyman Page here at Princeton. It's called ACT. And so I just wanted to show you two examples of such experiment, ACT and SPT, the South Pole Telescope. Those are competing type experiments, and what they are trying to do is measure the small scale CMB fluctuations, okay? And you can see, for example, I think even though this is from the competing group, the plot is nicer. So let's look at the SPT. It's the same plot, but it's just that when I had to shrink it and so, I mean, the measurements are slightly different, but it's more visible in this plot. So you can see the CL spectrum as measured by WMAP, and then you can see the CL spectrum continuing at higher and higher L as measured by SPT, okay? Same thing you conclude using ACT, okay? So this is one of the things these type of experiments, including the one we saw in the movie, are trying to do. And what is nice to see, or just one thing, if you look in the bottom, those are kind of the range of constraints on these various 6 parameters labeled with different names, but fine. Not so different, I guess. Maybe omega lambda is in the form of this theta, whatever here. But other than that, one thing to note is that, and these figures show the constraints on these parameters in 2 cases, when WMAP is used alone and when WMAP and these additional experiments are used alone. And I think what you can take away from this kind of, for the purposes of, at least of this talk, is that you know, the number of the peaks on the CL spectrum that these new experiments that have happened after WMAP have measured is comparable to the ones that WMAP have measured. So there was plenty of room for there be some discrepancy with the model. I don't know, the WMAP already fixes these parameters very well. You're predicting what you should see in these other experiments, and you're seeing a lot of these peaks that fit just fine. This just, I show this mainly because I wanted to show one example of the fact that we've already now had various instances in which things could have failed in principle. We are measuring new things, and the same 6-parameter model continues to fit. And in particular, I show this because it was the subject of this in the movie. But there are other observations that people have done, direct measures of the Hubble constant, or the supernova luminosity distances, or clustering of galaxies, or the Lyman alpha forest, and so on, all of which continue to be fitted very well by this simple 6-parameter model with the simplest possible initial conditions, and so on. And I suppose it need not be, it didn't have to be the case, okay? No evidence for the number of relativistic species pretty much for being anything different than 3. Maybe some marginal evidence, some people like to quote, but no real evidence for that. No evidence for the cosmological constant being, or the dark energy, or however you want to call it, for being anything different than the cosmological constant, and so on. So at least for the last few years, we've lived through a period of remarkable consistency between all of these experiments. And I don't think it needed to be this way, but it has been this way. Okay? Any questions about this? Yeah?
I don't know about the SPT trend also. The error bar at very high L is really small. Is that not intention with what just
Well, so you mean about the contamination from dusty galaxies. Indeed, the reason why the plot in the SPT one looks nicer is because they are not showing all of the machinations they had to go through to get rid of it. And while if you look at the ACT plot, you see all these other lines and so on. What are all of these other lines? It's all about these dusty galaxies, okay? So, indeed, things have been subtracted from this plot in order to make it, the contribution from the dusty galaxies, using their frequency dependence and some simple model, and the error bars there are supposedly taking this into account. But it's not, so I think perhaps a way to say it is that where these results not to have agreed, especially at the highest L's. If you look, it's better to look at the paper, but at the lowest L's on the plot, it's not such a big deal, okay? But it gets much worse fast. If this had not agreed with the simple 6-parameter model, probably people would, maybe the papers would not have yet come out, and they would be trying to find reasons why there is a problem or something. I don't know. But yeah, so I think it is true that at least this direction of getting more information by going to small scales with the temperature will face, a pretty hard stopping point in the not so distant future, because as you can see already from these ACT plots, and equivalent plots are in the SPT paper. I just didn't choose to show them. There's already significant work to get rid of that. Yeah.
So the 6-parameter model doesn't include massive neutrinos. At what level do you start to think that terrestrial measurements of neutrino mass become accurate enough that omega neutrino should be imposed in the prior?
We will go through the exact numbers in the lecture about large-scale structure, but if you just take so terrestrial experiments measure mass differences, okay? So if you just take the minimum mass, it measures two differences, and you don't know if there's a very small difference and a very small difference and a larger difference. So if you just take those differences and say take the lowest one to be very, very small mass, then it shouldn't have showed that contribution to, you multiply the number of neutrinos by that minimum mass that you know it has to be there, by having the lightest one be almost zero mass and then the two differences that you measure. We shouldn't have seen it. Not by much, but we shouldn't have yet seen it. One of the goals of the large-scale structure experiment is to get to that level, so we are sure that we should see something. Okay, but we are probably a factor of a couple short of that at the moment. Any other questions about this? Yeah?
If there was a modification to the Riemann equation, could then there be more parameters, or could the parameters differ?
Of course, if there was a modification that introduces more parameters, then there would be more parameters. So perhaps the zeroth approximation would be for people trying to entertain this idea, which let's say has not been a very at least successful program, but so far I think. But if it would be to try to find examples in which you add as many parameters as lambda CDM, that would be nice. So instead of having lambda, you have one other parameter. This happens, for example, or this was what happened, for example, in this DGP example. There was just one parameter, this RC, which it's just one parameter instead of lambda, and then those examples have equal chances of being ruled out, or you have equal amount of room to tweak around, because it's not the case that even so, with the CMB we have to live with this degeneracy, but we have a lot of other measurements. So in fact, forgetting about maybe it's not clear how you can forget, but forgetting about any possible problem with DGP, its claimed redshift Hubble constant relation eventually did not fit the data. So even if you don't want to worry about ghosts, and I don't know how you're going to live your life like that, but if you do, then you can just say it's been ruled out by the data. At least if you don't want to say, okay, we live in a curved universe with DGP, and then eventually you can live there. Any other questions? No? Okay, so what I want to do next, let me just set up the starting point for the next lecture. So this was an introduction, in what the next lecture will be about is calculating and talking about the cosmic microwave background, okay? So, and trying to get that spectrum of peaks, okay? So, good. So the most important thing to, the first thing, I guess, to understand what we observe is recombination, to understand the fact that the recombination happened. This is not, so what's the story? If you go back in time, the temperature in the CMB is hotter and hotter and hotter. The temperature scales as the 1 over the scale factor. Eventually, there are so many highly energetic photons, or energetic for the point of view of the 13.6 eV of the binding energy of the hydrogen atom. Backing up a little bit, most of the matter in our universe is in the form of hydrogen. That hydrogen was ionized, okay? So rather than being hydrogen atom, was proton and electron separated. But as time goes on, the temperature falls. Eventually, there's not enough photons in the CMB to keep hydrogen ionized. Hydrogen becomes neutron, okay? Now, the chances, the scattering cross-section for a photon against an electron, which is charged, is much, much higher than against a hydrogen atom. So by the time, when the hydrogen atom forms, the universe is neutral, and basically photons of the CMB can travel without being stopped by having to scatter with electrons, okay? And so 2 plots I have there. First is just as a function of temperature, the fraction of the hydrogen atoms that are ionized as a function of time or temperature, okay? Conformal time in the bottom, temperature on the bottom. And it's something that looks like this, okay? So very fast, it goes from being 1 to being 0. This happens at a redshift of around 1,000, okay, or 1,100. Very fast. 2 things to note. This happens then when the temperature of the CMB was a fraction of an EV. And already David told you this is not 13.6 EV, just because there are so many. The photon to baryon ratio in our universe is 10 to the 10. So even though the temperature is pretty low, there's still, at this time, it's when you start losing the number of photons to ionized hydrogen, much later than the 13.6 eV temperature. Other thing to note is that this is a temperature much, much below the mass of the electron. So this means that when we will talk about the scattering of electrons and these photons, we can just use Thomson scattering. So at this time, hydrogen is neutral. And at this time, hydrogen is ionized, okay? And the small correction to this plot is that, so what will happen is hydrogen recombines, the universe becomes transparent from the CMB photons, okay? And that's from where we will see the CMB. Furthermore, the regular matter in the universe, rather than being coupled through Thomson scattering with the photons and making this fluid of photons and protons and electrons moving all together, the regular matter now no longer has to worry about the photons and will start falling into the potential wells of the dark matter at this time. And so as time evolves, then this matter falls into these potential wells, forms the galaxies, the stars, etc. Stars start to emit UV radiation. This UV radiation eventually produces enough UV photons to what we call reionize the universe. So today we have very good evidence that the fraction of hydrogen atoms that are ionized in interstellar space or intergalactic space is very close to 1. Or it's 1, pretty much. So the photons of the CMB here were scattering with the electrons because the hydrogens were ionized. There was all of this period of time, sometimes called the dark ages by some cosmologists, in which, okay, everything was dark, but then the first stars turn on, they ionize hydrogen again, so again, hydrogen is ionized again, okay? But the universe has diluted so much that even though there's ionized hydrogen, if you just multiply density times cross-section, you will see that only a very small fraction of the photons actually scatter again. Okay, so this is, we can see that this happens in a variety of ways, but it doesn't block completely our view from the early universe. It could have, okay, but it did not. So there's another plot here, last one I want to show you, that shows this Hubble, the same as we had before, the Hubble volume, the Hubble scale as a function of time, okay? I mark there two special times, matter radiation equality, when this thing turns, the slope turns, and then this time of recombination at 0.3 eV in temperature, roughly. They're pretty close to one another. And this is good. It will turn out to be good because we are seeing recombination, matter radiation equality is pretty close, so it will affect things if we move matter radiation equality relative to the recombination, which is fixed by just the physics of the hydrogen atom. We cannot move the temperature at which it happens, given what we know about the CMB and the hydrogen atom. So this is fixed, but matter radiation equality could have moved around, but it's close enough that it's affecting what's happening at recombination, and so it shows up in the CMB, and that's why we can constrain omega matter h square. If it had been all the way on the other side, then we would have no sensitivity, or much before it would also be not so good. And the other thing that I plotted in the dashed line, the last thing that I'll show you, is the mean free path for the photons of the CMB. So as I said, the photons of the CMB scatter with the electrons, basically Thomson scattering, so you can ask the question, what's the mean free path? And you can see the cross-section is fixed. If the universe is Thomson scattering cross-section, if the universe is fully ionized, then the number density is just growing, diluting as a to the minus 3. That's the beginning of this curve of how the mean free path goes as a function of time. But you see that it very rapidly shoots up, okay? The dashed line very rapidly shoots up. This is nothing other than all of the hydrogen atoms, all of the electrons are going into hydrogen, so they cannot scatter the electrons anymore. And very quickly, you can see this line going above the line of the horizon, the size of the horizon. In other words, the mean free path has become larger than the horizon at the time, so photons are not even scattering once as they travel one Hubble time. So that's when the universe becomes transparent. Usually the time when that's happened is called decoupling, to distinguish it from the time of recombination. So as you can see, the Thomson scattering cross-section is sufficiently high that you have to go quite a while down this x going to 0 until the mean free path becomes larger than Hubble. So recombination, if you want, starts when this line starts going up fast, and it takes a little, in time it doesn't take very long, but it takes, the hydrogen has to recombine quite substantially in order to decouple, what we call, which is the moment when the CMB photons just can do whatever they want. Okay, so we are going to basically study this time and the leading to this time in the next class. Thanks.